So yesterday they were dependent. We had two sets, they were related. When I'm looking at independent, they don't have to be related in any way, shape, or form. I might have two different people that go out and conduct a study and they get two different samples. They could even be different sized samples. And so what we want to do is be able to compare the means from each of those groups. And so it will be slightly different because we can't just find the difference. We're not guaranteed to have the same number of points in each. So we'll have to look at the two means as separate things. Now again, like I said with yesterday's, we can do them by hand, but we were really relying on our calculator quite a bit for doing those. So it's the same with these. I will show you how to do it by hand if there's someone that likes to do it that way. But these problems, I will not say that you have to do it by hand when you get to a test or quiz. So you would be allowed to do these solely on the calculator, just like yesterday's. If you do pull out your formula sheet, we are in chapter 11. And the first bullet in the top of the second column says a test statistic for comparing two means of independent samples. And so this is how the t-value is calculated. It looks a little more scary, but what it's doing is it's taking two different sets. So this is like saying the sample mean from the first, the sample mean from the second. This is the mean of the first population, the mean of the second population. Standard deviation of the first set, the number in the first set. Standard deviation of the second set, the number in the second set. So the ones and twos just tell you if it comes from the first set of data or the second set of data. If you think about when we found a t before, we just did x bar minus mu divided by s over n. So it gets a little more complicated because we have two x bars, two mu's, two n's, two standard deviations in here. As far as criteria, what I expect, we have to have all the same things as usual. The main thing, anytime we're dealing with a mean, we know it has to be normal or n has to be bigger than 30. So that would be the one criteria that I might ask you to verify. Since we have two samples, we need both of them to be bigger than 30, not just one. Or both of them have to be normal, not just one. As far as the hypothesis testing, we know our null hypothesis is always equal to, and our alternative we can do less than, greater than, or not equal to. We will be comparing the means from the two sets. So the null hypothesis would be that the mean of each set is equal. And then the alternative, the means aren't equal, the mean of the first is smaller, or the mean of the first is bigger. And those are the different options. So then hypothesis testing is like before. We have to write our hypothesis, we have to find our alpha, we have to get t, and then we can use the table, or we can use our calculator. We tended to go with the p-value approach where we just get the probability, and if it's smaller than alpha, we can reject. So let's look at a problem. Again, part of the reason that I will do these on the calculator is because a lot of times we have the original data. And if you're already entering everything in your calculator, it seems silly to then turn around and do the test by hand. So this one, we want to know if state quarters had a weight that is more than traditional quarters. So we have 18 state quarters and 16 traditional. So that's your first clue that it's not matched pairs, because could we even do the difference on these? No, if you try to on your calculator, it's going to shoot back an error because we have different numbers in each set. So we want to test the claim that state quarters have a mean weight that is more than traditional. So my null hypothesis. We're going to treat state quarters as the first group and the traditional as my second group. So what's my null hypothesis going to be? The mean of the first equals the mean of the second. The alternative hypothesis.
Mean versus greater than mean.
Since I made my stakeholders the first group and I want their weight to be more, so mean at first is greater than mean at second. Okay, now enter all this. So on our calculator, what we're going to do is go into stat, tests. We know that anytime we're dealing with a mean, we're looking at a t-test, but we can't just do regular t-test because we have two different sets. So what we actually want is number 4, the 2 sample t-test. So stat test number 4. Okay, are we basing it off data or stats? Data, because we entered our data. Your list 1 should just say L1. List 2 should just say L2. Frequencies are both 1, and we're not going to change that. We are testing greater than. Pooled should say no, just go down to calculate. All right, so it even tells you up at the top, mu1 greater than mu2. So we can kind of confirm that's what we are testing. So my P is 0.00886. And I probably should have wrote down my T as well. T is 2.5367. Okay, those are the 2 things that I've asked when you do it on the calculator. Write down your T and your P so I kind of know what you're looking at and what you're basing your answer off of. We know that we reject if P is less than alpha. Alpha was 0.05, so since P is less than alpha, we reject the null hypothesis. What that means is there is enough evidence to conclude the state quarters way more. I know I told you that you can do these on the calculator, but would it be okay if I walk through how to do it by hand? I'd like to show you that, even though it's not my expectation that you do it that way, but just so you can kind of see where it's coming from, and if you are one of those people that don't like doing it on the calculator, you have that option. I did include a couple blank slides after this, I think, so you should have plenty of room to show how to do it by hand. Again, a lot of times these values are going to be slightly different depending on which approach you take. So if we look at that T statistic formula that I gave you, we need a lot of different things. We need the mean of the first, the standard deviation of the first, the number in the first, and we need all the same things for the second. How can I get that stuff? It's all entered in my calculator, right? The 2 sets of data. So if we go into stat, calculate, and we need 2 variable statistics because I have both variables in here. So we need to change my X list should be L1 and my Y is L2. Oops. Yep, it's not going to let me do it. I'm going to have to do one at a time because we have different numbers in. Okay, let's just go stat, calculate 1 variable statistics. And let's run it off L1. Okay, so the X bar is 5.7022. Standard deviation 0.0497. The number was 18. It does not give me the mean of the whole population there, so I don't know mu of the first. Let's repeat this for my second list, so I need to do one variable statistics again, but this time I'm going to make my list L2. So the mean of the second is 5.6494. Standard deviation of the second, 0.0689. And the number in the second set was 16. In all of these, our null hypothesis is that the mu of the first equals the mu of the second. So, if you think about in the test statistic, it asks for mu1 minus mu2. If those are equal to one another, what do you get when you subtract them? 0. So then our formula for the t. So it says x bar sub 1 minus x bar sub 2. So the first x bar minus the second x bar minus mu of the first minus mu of the second, which we just determined our null hypothesis is that those things are equal to each other, so when you subtract them you would get 0, divided by the square root, standard deviation of the first, squared over n of the first, plus standard deviation of the second, squared divided by the number in the second. So then I have to put all this in my calculator. Did you guys get it? What'd you get for your answer?
2.5347.
If you did not get that, let's troubleshoot. If we think about our critical value, okay, when we do our statistic using our t-table. So the critical value here, what was our alpha level? 0.01. Was it? Or no, 0.05. Okay. So if you go to your table, so we have the 0.05. The degrees of freedom, you have to go with the smaller. So we had an 18 and a 16. We have to go with the 16, so degrees of freedom is n minus 1, so 16 minus 1 would be 15 degrees of freedom. We were testing greater than, which is what this table gives us. So if we go to 0.05, 15 degrees of freedom, the t statistic is what?
1.754.
So we know then that means if you're in the shaded region, you reject. So since 2.53 is in the shaded region, reject the null hypothesis, which is the same conclusion we got from our calculator. It's just a lot easier to let our calculator do the work. Questions? We have also used confidence intervals to decide if we should reject or not. So we know we build the confidence interval based off our sample, and then if the null hypothesis is included in the interval, we would fail to reject. If it's not, we reject. So let's talk about the confidence interval when we have these two different samples. So it's kind of similar to the confidence interval for one sample. You're used to doing your mean plus and minus the t times the square root of s squared over n. But what you have to do is subtract the means and add your standard deviations together. Again, I will show you how to do it by hand, but you can use your calculator for this if I ask you to create one. So let's say I wanted a 95% confidence interval between the means for these two quarters. All right, so on our calculator, we will go to Stat, Tests. We know if we're dealing with a mean, we need to be looking at a t-value. We want an interval, so we're used to just going to number 8, t-interval. But this is different because I have two samples, two different samples. So if we keep going down, 0 is a two-sample t-interval. So we're going to go to Stat, Tests, 0. All right, we're going to keep it off data. If you did do stats, just to show you if you have one, what you'll have to do is pull in the mean, standard deviation, and number from each of the two sets. So that would have to be given in the problem. But we have the data that we already entered. So list 1 should be L1, list 2 is still L2, frequencies are 1. My confidence level, I wanted 0.95. So if we calculate, you should get, did you guys get 0.0101 and 0.0956? Did you get the same thing we had before when we ran the first test? Did you get the same and this one, did you get those values on your calculator? In your data? So these weren't exactly the same? Okay, then your data is all. Okay, so what does this mean? The null hypothesis is that the two means are the same. Okay? If they are the same, then what should you get when you subtract them? 0. So if 0 is in our interval, that's like saying they are the same, so we wouldn't reject. Is 0 included in this interval? No. So since 0 is not in the interval, we would again reject the null hypothesis. This interval is talking about the difference between the two. So just like we said before, if they are equal, then when you subtract them, you should get 0. So we're always looking to see if the 0 is in our interval or not. would like to show you how to do this one by hand as well. Just be, you have, I think I put a blank slide after it. So you should have room. By hand, it will be slightly different, so just keep that in mind. We need, for our formula, T alpha over 2. So alpha was 0.05 because we were doing a 95% confidence interval. So that's 0.025. Our degrees of freedom, we already said n-1, you have to go with the smaller set, so it's 15 degrees of freedom. So if you go to your table, 15 degrees of freedom, 0.025, the t value is 2.131. So our formula, mean of the first minus mean of the second, plus or minus the t alpha over 2, and this is on the formula sheet. Okay, so looking back at our slide where we had all this written down. So x1, the mean of the first was 5.0 or 5.7022 minus should be a subscript 5.6494 plus or minus 2.131 square root standard deviation of the first set squared over n standard deviation of the second set divided by n. So the interval is a little bit different, but we